Hello everyone, welcome back to Bytes of CSE. So here we are at the part 3 of K nearest neighbor algorithm, and in this lecture we will discuss that if different distance metrics have any relation with the accuracy, and there will be a hands-on tutorial on handwritten digits from MNIST dataset. It's a classification, so we'll be using K nearest neighbor classifier. So when it comes to distance, there are so many distances that are used in artificial learning and data mining, deep learning, data science. So there are basically 54 distances from 8 distance families. And what you're seeing here is basically just not even the tip, but I'll call it the tip of iceberg. Now, this is not focused on the different distance metrics used in data science or artificial learning. So I will not get into much detail about it. You can just take a screenshot of this one. So these are very commonly used distance metrics used like Euclidean and Manhattan. These two are readily available and usable in your scikit-learn library. Then we have cosine similarity. This is used in recommendation system. Minkowski is bit of a generalization of these two. And then we have different distance measures which measures the difference between components of two distance. We have Chebyshev Hamming distance. I think you have come across this Hamming distance in your computer networking lectures. Then we have string similarity distance measure, Akkad similarity, which finds a similarity between sets. Then we have a dice similarity also, which is used in biology or genetics data set, and so on. So I have actually gone through a number of research papers which has discussed the impact of distance matrix in KNN, and the data set that we used was mostly from this UCI machine learning repository. So these are the data sets mostly used in these studies, and what I will present to you here is the crux of whatever has been discussed. So point number 1, Euclidean and Manhattan distance, which is the most commonly used distance metric in KNN, they gave a very good accuracy for like over 80%. So the minimum accuracy was 80% for all the data sets here. So we have already covered Euclidean in the first lecture, I guess. And this is the formula for Manhattan distance. So this just calculates the absolute distance between two vectors or 2 points. Then we have Lorentzian distance, which gave which really worked well with real data, and it gave a accuracy of over 97% on the vowel data set. So Lorentzian basically is represented by natural log of absolute difference between two vectors. So this distance is basically sensitive to small changes, since log scale expands the lower range and compresses the higher one. Then we have the Akkad distance, which worked well with positive integer data like letter recognition data set, which gave over 95% accuracy. And Akkad basically gives a dissimilarity between two sets based on union and intersection. And then we had Canberra distance, which worked well with positive real data like the Australian here. Where is Australian? Here. Like the wine data set, the Australian data set. This really gave good results. And Canberra is sort of a weighted version of this weighted version of this Manhattan distance. As you can see, the similarity between the equations. So the only difference is here the absolute difference between two vectors x and y, as shown here, they are divided by the sum of the absolute values before this outer summation. So this is basically, it works well for data which is scattered around the origin. But there was one distance measured which outperformed every one of them in every data set, and that is Hassanat distance. So this obtained the highest accuracy of all in all the data set. So this basically finds the non-convex distance between 2 points. So what is a non-convex distance? Suppose there are 2 points A and B, and you draw a straight line between A and B. So in case of a non-convex distance, it will be that this entire straight line or parts of this straight line will not belong to this space. So from a observer's point of view, you can say that this actually won't look like a straight line. If you are watching from your space, it will look like it's bend around some hindrances. It might have very complicated contours, and this distance calculation, this is kind of a more nuanced distance calculation. So there was a paper on this which was specifically to enhance the performance of nearest neighbor classifier. So I will not discuss Hassanat distance much in detail, or rather in detail at all. So I will leave the link to this PDF in the description box. Please do check it out. And now I will move on to the hands-on part. So I have used the MNIST handwritten digit data set. So this is the Kaggle link has been given in the description box. Please check that out. So I have used the training data set in the hands-on tutorial. So let's move on to that. Hello, so let me start with applying K-ring classifier on handwritten digits dataset by MNIST, and I have left the link for this dataset in the description box. Do check that out for downloading the data. So I have used the train dataset to show you how effective K-ring is. So now let's start with the library import. So first, let me import NumPy as NP. Oh, and one more thing, I am using my local, I'm really bad at coding and talking. Anyways, I'm using my local, or shall I say, Jupyter Notebook. But I will highly recommend you to use Google Colab, because you don't have to bother about the libraries, compatibilities, and installing so this and that. So you can straight away do that. And if you are guessing that how to use, like upload, if you are new to Colab, in fact, you don't know how to upload a data set and things like that, for the basics, I have an article on Medium. It's not basically a basic thing, but I was actually doing a tutorial on, I think, text to speech. So I have given an in-depth tutorial on how to actually use Colab there. So you can go through that. That will also be given in the description box. So now let's get into this. So pandas, now we will import matplotlib to pyplot as plt, and then the sklearn things like from sklearn dot model selection import train test split as TTS. It becomes easier rather than writing train test split every time. From sklearn dot neighbors import k neighbors classifier as KNC, and we need some metrics. So from sklearn dot metrics import accuracy score, that's to measure the accuracy of the model. So oh sorry, import pandas as PD. Now let me just get the data set. So into the data frame, so df equals to pd dot read CSV, since it's in a CSV format. So here my name of the file is handwriting train.csv and df.head. Let me see the first 5 columns, and okay, we'll just wait for a while before we can actually move into the next part of it. Okay, so there are 785 columns. Let me just see how many rows, how many columns. Let me just go through that using df.info. Let me just find out. So there are 785 columns and 42,000 entries. Now here what happens is, see, the first is the label 10 whatever, and from here to here there are actually 7, from pixel number 0 to pixel number 783, so 784 pixel. So what they have used here is, it's basically a 28 into 28 image. It is supposed to be a matrix. This is a grayscale image of that handwritten digit. It is from 0 to 9, I think. And so this matrix has been flattened to a vector. So 28 into 28, that gives you 784. You can see it yourself. Okay. So basically this is the label and this is the image which has been flattened to one dimension. Yeah. So now let me, since there are like 42,000 entries, I'll just be dealing with 5,000 entries better, because things really go slow if I work with 42,000. So let me just take values, just the first 5,000 I'll take. And now I will split this data into target and the features. So I'll go by the general convention, that is X for the features and Y for the label. So let's do that. X, Y equals to data. Now here we will consider all the rows in case of this X, but we will just rule out this label column. So in order to do that, all the rows are selected and just the first column is like removed, and in this case all the rows are selected and just the first column is selected in case of Y. Oh, what is there? Shows a syntax error. Oh, sorry, forgot the data. Anyways, now let me just check what about the data distribution, because the distribution of the classes is very important in case of k-neighbors classifier, right? So in order to do that, let me just have to do a bit of let me take that in a data frame, that way it becomes easier. pd.data frame, and we'll just take the Y column in the data frame and we'll name the column as target. And now we'll see that what about the data distribution of this target. Basically this data frame contains just one column, value counts, This is optional. It's just to show you that how the data distribution is. Okay, let's wait for a while. Oh, has to be columns. Sorry. Okay. So number 1 is 558, 2 is 545, 6 is 516, 7 is, this is actually a sorted list anyways. 0 is 494, 3 is 480, 9 is 478, 4 is 477, 8 is 477, 5 is 469. So you can't, in case like it's a real world data set, so that way I'll say that this is more or less a balanced data set, so we can use KNN classifier over here. So now let's get started. We'll split the data set into the training and the validation or the test set. So let's do it using the train test split. So X train, X test, Y train, Y test equals to TTS. That was the short form I used for train test split. So we have X, Y. Let me keep just 20% of the data for testing. So test size is going to be 0.2. And let me just add a random state in order to just replicate 111. Let me just do that. And now let me now I'll call the KNN, that is KNC, and I'll take the number of neighbors as 1. Now if you're wondering why am I using one neighbor, I'll show you shortly, because that is something again I'll have to show you. I have gone through that part 2 of the lecture, how to find the optimal value of k. Now I'll show you how to do that in practice. I just mentioned about it, right? So knn1 dot fit, I need to fit this X train and Y train to it. Okay, and now I will predict the labels for the test set. So let that be Y pred equals to knn1 dot predict X test. Now we'll have to find out the accuracy score, like how accurate the predictions were. So since there are 5,000 data points, so and we are using 20% for the test set, so 20% means there will be around 1,000 data. I think, yes, there will be around 1,000 data in your test data set. So let me see how far or how good or bad it did. So let's find the accuracy score. So score equals to accuracy score Y pred. That will be checked against the original label, that is Y test. Y test print score. 0.924, that is 92.4% accuracy. Now imagine we have tried KNN on an image data set, like image and a corresponding label. We haven't used deep learning, we haven't used like any sophisticated now we have just used a very simple, humble machine learning algorithm like KNN, and that gives us 92% accuracy. Now let me just plot a few of those test points and see. Now let me just take the first 10 data points. Yeah. So test data, and I'll just plot the image and show that how good or bad it fared on those first 10 data points. So test data, let me just take the first 10 rows. All the columns will be selected, and the, what should I call it, true label, just the first 10 labels. And now we'll see how it fares for each of the data points, the test data points. So for I in range test data dot shape 0. Shape 0 gives the number of rows. In this case, it is 10. And image equals to test data dot reshape 28. Now what am I doing here? See, 784, so it's a flattened vector of one dimension which contains 784 values. Now I am reconstructing the image matrix from the image vector. So I am reshaping that. So it becomes a two-dimensional thing now, because I will be plotting this one to actually reconstitute the image, the original image. Okay, now then we will, let me print the true label. True label. Let me just put an format sign here. Okay. Sorry. True label. It is going to be y test the ith one. And then we'll print the predicted label. Let's add this one here. Okay, predicted label. It will be knn1 dot predict what? The test data point I. And now since there is just one data point, I will need to reshape that to 1 minus 1. That's the convention. Yeah. End it here, and finally this. I hope these are matched. Otherwise, okay, that will give me just a syntax error and just have to. Anyways, plt dot figure, plt dot image show will show the image, and the color map will be gray. It's basically a grayscale because all you can see here is the values are zeros and ones. Unfortunately, there is no one here. Anyways, values are all zeros and ones, and that is when we use a grayscale image, we use a binary. We have to convert that to some numeric value, right? So we are using that binary value 0 and 1 to show the color thing. Plt dot show. Cannot reshape. 7840. Just a moment. What's happening here? Just a moment. Let me give some time. Oh, sorry. Test data I missed that out. Sorry. Okay. Now it's coming. Let me just have all the 10 things and then. Okay. So here we have the true level as 2 and the predicted level is 2, and this is the image for the first one. Next one, the true level is 9, the predicted level is also 9, and this was the picture. Third is true level is 4 and the predicted level is 9. So this is how the picture looks like. So, well, even I would have been confused if it's a 9. This is the true level is 3, predicted level is 3. So this is how the picture looks like. True level 9, predicted level 9, this is how it looks like. True level 1, predicted level is also 1, this is how it looks like. True level 2, predicted level 2, this is how it looks like. True level 6, predicted level is also 6, that is also fine. True level is 0 while the predicted level has been 6. So this is what the image looks like. This is pretty hard to predict, right? Who would know that this is a 6? True level 1, predicted level is also 1. So among these 10 samples, 8 have been correctly classified. So an 80% accuracy for this part of the data set. So not bad, right? And this is really difficult to understand that this is a 6 and not a 0. Sorry, this is a 0 because of this. It's been protruding something. And this is also very close to 9, right? So it's not bad at all. Not bad at all. Now, the last thing that I'd like to show you is why did I choose the number of neighbor as 1. So I'm putting practice to what we have learned in the second lecture. So let me find out the upper limit for that k, which is the square root of the number of data points. So, for this I will need to import math. Upper limit is equals to math dot ceiling, math dot square root. Ceiling is just to make sure that it gives me back an integer and not some decimal. Okay, math dot square root, that would be x train dot shape 0. Shape 0 is the number of rows, that is number of your examples, and columns is actually shape 1. This is this. Okay, now let me consider two vectors, k vector that will hold the values of k and error vector that will hold the value of the corresponding error that was incurred from that k value. Now let me start that for loop for k in range. We'll start from k equals to 1, that is number of neighbors equals to 1 2 upper limit, so it will end just before the upper limit, and that is the reason why we are using the ceiling function. So let me call the k in c in neighbors will be equals to k. Next we will be fitting knn dot fit x train y train. Let me just x train y train, and then we will find the score, the accuracy score. I'm not using a YPRED, I'll be directly score, knn dot predict y test, very sorry, x test, it would be x test comma, the y test value, and then since we are finding the error, it will be 1 minus this score, and now we will append the value of k into the list. K vector dot append k, err vic dot append error. Now this will take some time. Let me just write the plotting function while it executes. Plt dot figure, plt dot plot. So your x will be the k value. So your kvec is going to be the x and your error is going to be the y. So first goes your x and here goes your y. Error vec. And let me just add some name to the x label, that is number of neighbors. plt.y label is error, and let me just add some title to the plot. Neighbor versus error. Okay, so this has been done. Let me plot. All right, actually I was keeping this one handy. Oops. I was keeping this one handy just to make sure that if something, my machine was actually running slow, so if something goes wrong, I'll just be able to show you the plot in any case. So thank God it did execute on time. So this is like when you are using the first neighbor, this is your error, which is less than 0.08. And as you increase the number of k or number of neighbors, your error is basically escalating. But even in the worst case, that is a little bit more than 60, because 60 into 60 is 3600. So for 4000 data points, it will be, I don't know how much it was. Let me just find out what ulim was. 64. Okay, so it gives you a plot from 1 to 63 actually. So this is for 63 neighbors. Even for that case, it is less than 0.15. That is, the accuracy is more than 85%, even if you consider 63 neighbors. Okay, so since this gave me the lowest k, that is the reason why I had chosen this nearest neighbor as the number of neighbors as 1. So that is also a bit of a bonus that you receive, that how to find the optimal value of k. So if you want me to share this particular notebook, do leave me a comment. I will share the notebook. I preferably share the collab, so it becomes easier for you to straight away use it. And that's all for today. Do check the description box, and thank you for watching.